Hello, it's James from XRobots.co.uk. This is part 2 of version 2 of my BB-8 Droid prototype project. I made a previous version where the head actually balanced on the ball, which I started building before Star Wars Celebration at Anaheim, before the real BB-8 rolled out on stage, so I hadn't seen that at the time. And now I'm working on a new version which is more like that version. So in the last part I pretty much started working on this. In fact, this video is being made in the past. It's currently early October and I'll be releasing this in the future sometime, probably around November or December. So I've done quite a bit of work on this already. I've already had the ball has been made here, which is entirely 3D printed. Basically the internal hub turns, and then I have a flywheel that turns in the middle, which causes it to rotate in the opposite direction. And last time I worked on this Bluetooth controller, so I can make a custom controller with whatever buttons and knobs and things I need, and I can send those values over Bluetooth, and that also means I can pair to the Droid with a phone in the future and write a phone app. So at the moment I can control this to rotate by spinning that flywheel, and that works quite well. But as I demonstrated last time, the problem is basically driving this along, and the internal hub rotates. There's a big wheel in the bottom and that causes it to shift its mass to one side and drive along. The problem is of course that the inertia catches up eventually and causes it to kind of drive along in a jolting fashion as the mass catches up, and then the internals drive faster again and so on. So this time we're going to look at an inertial measurement unit to stabilise the inside, hopefully. And since I've already built one droid with a head that balances on the ball, I can probably make the insides of this balance on the outside, because it's much easier, because it's effectively inherently stable and stands up by itself rather than repeatedly falling over. It does, however, have quite a lot of wobble in all directions. So I'm really hoping that stabilising it in one axis is going to kill a lot of that. But we'll soon see. Here's my Arduino and its Bluetooth shield, which is receiving the signals. I've got a little board here which is basically a power breakout board for 0 and 5 volts and 3.3 volts. I've got a motor driver here which is the same as the one on the other side for the two motors that turn this flywheel. And I've got another motor driver inside here which is a big one, and I'm running a windscreen wiper motor on 24 volts which will drive the whole hub round. Which is definitely enough power to power it. So we're going to put an inertial measurement unit in here today on the internal hub, and this hub turns against the outside wheel, so that can drive a constant angle rather than a constant speed, which we'll try and hit, and it's going to use a PID loop to try and keep that constant and drive along without wobbling. I'm also going to put one inertial measurement unit in the future on the head stick that pivots about this point, that will move the head backwards and forwards. And the reason for that is so that I can take that data, combine it with the inertial measurement unit fixed to the body, then I can work out the absolute centre of gravity of the whole droid. Obviously when the head moves forwards, it's going to cause it to tip forward slightly, but I want to compensate by moving the internal hub back a bit, and I'll use both inertial measurement units summed together with a multiplier to try and work out what that centre of gravity is. The sensor I'm using this time is an Adafruit BNO055, which is a Bosch part, and Adafruit have put this on a breakout board and written an Arduino library that's part of their sensor library suite. This is really good actually, because it does lots of the maths for you. When I did my ball balancing version of BB-8, I had to do stuff basically to combine the sensor data from the accelerometer and gyro and use arctan and all sorts of complicated things to try and actually work out the absolute angle I was getting from it. This board does all the maths for you, it just gives you the angle, which is really, really good. So it takes a lot of processing off my 8-bit Arduino. All I need to run on there is a PID loop, which will be quite easy to do. So this is wired into I2C on an Arduino Uno. The other end of it is going to my laptop, and I'm running the example sketch for this, which is pretty simple. Hopefully you can see all of those angles spinning past. So as I rotate it, the one on the left there changes, which is mostly using the magnetometer to work out how much I'm rotating it. The other two are the pan and tilt. So as I tilt it, you can see those angles changing. There we go. So that's pretty good. The code is basically just saying give me the numbers. and there we go, just gives you the angle, so that's really, really good. So I think the tilt is only going to be about plus minus 30 hopefully in one axis to start with, although I will be using the other one for side to side stabilization, which I think is going to use the head stabilizing side to side to keep it on balance. So I'm going to get this wired in, write a little PID loop, and we'll see how stable it is. Here we go, so I've fitted my inertial measurement unit, which you can see just mounted just here. And that of course is using an accelerometer, gyro and magnetometer all mixed together on the board to provide me the angle. So this is powered on at the moment, and you should be able to see if I push it this way, the internal hub catches up and drives along. So it's a bit like a camera gimbal in a way, in that if I do this, the internal hub catches up. So it's taken a bit of tuning. It's not quite perfect, but it's pretty good. So of course that kills the wobble as much as it can. If you look at the ball, obviously the inside moves a little bit to try and stabilise. So if I turn this off, you can see we get this sort of thing, and if I turn it on, then it stabilises itself out. And it does mostly an okay job of it. Now there's a couple of dirty hacks. So I found that if I spin the lot of metal here, it really confuses the magnetometer part of the sensor and produces a bunch of data that isn't really there. So for a little while afterwards, it'll then drive off in one direction because it's affecting the angle it thinks it's at. So what I've actually done is locked out driving for 1.5 seconds after spinning this. So if I do this, now we've got no drive for a bit till it turns back on again. So basically the only way to drive this at the moment is to drive in straight lines, then turn on the spot, and then drive again in a different direction. So it's a bit nasty, but basically steering and driving don't really work well together anyway, because when this is driving, it's offsetting this weight to pull it forward, and that means then that spinning isn't actually sort of perpendicular to the ground anymore. It's off centre, which causes the ball to spin off and tip over. So it's actually much better to lock out the driving whilst I'm turning on the spot and just use that, then drive along, stop and then turn. Anyway, I'll show you the code and then we'll give it a quick demo. Here's some Arduino code that's running on the Droid. So I've got various libraries included in here. Wire for the I2C, the Adafruit sensor library, the Adafruit BNO055 library, which is for the sensor, the PID loop. I'm also using the servo library to drive that big motor controller because it works as an RC servo. So there's lots of things defined at the top. Some of these are the PID variables, and I've also got my PID being declared here, which is one PID loop at the moment. I'm using UART serial actually to read the data over Bluetooth because that worked much better than software serial in the end, and that's initializing the sensor. So if we look down here, we've got some of the PID settings that center around 0. And the PID sample time is currently 20 milliseconds, which is the rate it's receiving new data. I'm reading the data using serial parse int, which is looking for the data in the serial stream separated by commas, and when it gets the new line character it knows it's got all of them. So I've got 2 buttons on my remote, and those are followed by the 4 analog channels, which are the 2 sticks. In fact 5 analog channels because I've got that knob to turn, which will be for turning the head hopefully as well. Further down we've got the code that drives the flywheel, so that's just reading channel 1 on the remote, which is the left to right direction on the right hand stick. And basically there we're driving 2 analog channels, so we've got a variable speed on 5 and 6 that are driving the L298 controllers. One is for one direction and one is for the other, and at the end of both we're bookmarking the time here, so I'm using the multitasking stuff. Look at the Adafruit Arduino multitasking examples. So I'm bookmarking the time, and that's used further down. So basically this locks out the drive for 1500 milliseconds after spinning the flywheel. So we've got this part here that says basically if the time has expired then set that flag to 0, and if the flag is 1 then still lock out the main drive. So once the flag is 0 and the main drive is enabled, we then use the PID loop, which is here, to drive that main axis. So it's using the BNO055 to get this sensor data, We're using channel 0 in fact as the set point, so that is setting the angle from the drive stick on the remote. It's computing the PID loop and then off it goes. My PID loop variables are sort of fairly basic, so I'm using 1.2 as the proportional gain. The derivative is only set to a very low number, otherwise it jitters a lot, and the integral I'm not using at all, as I didn't really use it in the ball balancing robot. So that seems about right, and it seems to work quite well. I've got a thing here, we've also bookmarked the time. Every time we receive data, we bookmark the time. And if there's no data for 100 milliseconds, then this is the safety section, and it writes all those motors and turns them off. So if the remote becomes disconnected, there isn't still data in variables driving the robot, it's actually setting them to 0 and low, so it turns off all the motors. So if I turn off the remote while it's driving, the robot stops within 100 milliseconds. So let's give that a test. So obviously now we get a much more stable drive. If I try and stop suddenly, you can see the internal stopping suddenly, but if you watch the ridges on the ball, you can see in fact that that's quite a gradual stop, and it doesn't wobble too much. If I slow down gradually, then I can get this to drive quite well under control. I can still spin on the spot now. You can still see the wobble side to side, but there's not much we can do about that right now, so let's just drive over here. So on the whole, this is much more controllable than it was. There we go, nice and smooth. And the inertial measurement unit is effectively dealing with that deceleration, because even though I'm giving it a set point of 0 when I let go of the stick, it's saying, hey, I'm falling the other way, so it's giving it some more currents into the motor and slowing down gracefully. So this is quite good. You can still see this side-to-side wobble, but we'll come on to that later. So that should be pretty good. And as I said before, the head itself is going to have its own stabilization, so even though the internal hub isn't particularly graceful looking, still wobbles a bit when you slow down, the head itself is then going to be stabilized on top of that. So pretty happy with this compared to how it was, even without being able to steer, which may be solved partly by leaning the head. But it's a much smoother ride, so I'm much more hopeful this is going to be successful. So let's talk about this head mechanism. So there's going to be an arm that moves around inside, and it has to pivot from the very centre of the ball so that it tracks the radius correctly. So that piece I'm going to do in the next episode, but for now I'm actually going to make the magnetic coupling and the actual sort of head chassis. So I got hold of some roller balls. These are 1-inch plastic roller balls, and they're in a socket. And inside there's 3 little rollers that support it. The problem is the balls are solid plastic, so they're quite noisy, and also depending on which way the ball is rotating, or at least most of the time, it's always rotating the wrong way against one of the rollers, so there's quite a lot of friction. So in fact, it doesn't actually feel like the ball is even rotating there, it's just scraping the surface. You can feel it rotating on a slightly more grippy surface, and I would put rubber or something on the ball, but then obviously it won't turn on the spot as well. So effectively this is just skidding over the plastic, which isn't very good. Now you can get better roller balls which have sort of more bearings in the socket, and some of them have a little caster above that the ball rolls on, and those are omnicasters, but they cost about 20 or 30 pounds in money each, and they're quite heavy, and the balls are still solid plastic. So what I really want is something rubber that's a bit more cushioned to reduce the noise. So what I'd really like to do is run the head on big rubber wheels, which would be great in one direction, but obviously it needs to move the head sideways slightly to stabilise, and it also needs to rotate. So I'm actually going to 3D print my own special solution. The plan is to 3D print my own special casters with NinjaFlex rubber wheels, which you can see I've done here, and I've done some work on working out what the angle is going to be for those. for a particular spacing, because obviously this is the surface of a ball, so they all need to sort of track the surface of the ball properly, pointing down into the centre. So that's about 15 degrees. On the chassis here that's green, I've moved them to about 13 degrees because I've moved them slightly closer. And I think that's about right for a half-metre diameter ball, so they always point directly towards the centre. Now there's another part to this. So as casters reverse direction, obviously the wheel has to swivel all the way round the other way, which causes some sort of sideways loading and makes the thing sort of move slightly around in that sort of circular direction as the caster rotates, and there are 3 on here. Plus they're on the surface of a round ball, and the head needs to move in all directions, so it needs to move sideways, backwards, forwards, and it also needs to rotate. So what I've done, and I'll demonstrate why when I've printed this, is put an additional rotating section which will have more bearings right through the middle of this, so the head can rotate without the casters moving, or the platform with the casters on can rotate without the head moving. So I'm going to print this all out and I'll demonstrate why that's really necessary when using casters for this sort of assembly. Here are all my parts printed out, so I've started to assemble the casters. So they've got bearings that cause them to rotate, and they've got the wheel is just on a 3mm shaft with some washers, but they're pretty fast. Whoops! So yes, I'm missing a bearing, which I've got some more bearings due to arrive, which are 6mm inner diameter bearings. So I've just got a bolt bolted through that way. There's a bearing in the bottom, then there should be another bearing in the top there, and a nut which I'll eventually put some thread lock on to hold it. So these work really, really well, and of course they fit in this plate and they're all angled in slightly. And these are going to get screwed in so that they all face in and match the sort of radius or the circumference or whatever of the ball, all pointing towards the centre. Then within the middle of this, I've got this other piece which goes top and bottom, and that's got 8mm bearings in, and that's to allow the head shaft to rotate, or this to rotate around as it's moving but keep the head still. So let's put this together and I'll explain why that's important. So here we go, I've got this assembled now, and I've got a bolt through the middle here that rotates independently, and that's going to have a plate on the bottom with at least 2 magnets in it, which grip through the ball. So on the inside of the ball, on the arm, will be another magnetic plate with the 2 magnets which guide this around on the top. So now I've got these rubber wheels on, it's quite smooth moving, but you'll notice that it has a tendency to rotate as I change direction, and that's because the casters want to sort of swivel round on the bottom, which causes some sort of rotation in this as it goes. So I could, obviously this can rotate around, so for head rotating that's no problem, but for changing direction it puts additional friction on, and I want this to be as smooth moving as possible so the head doesn't sort of lurch along as it goes and doesn't cause too much friction, slowing down my dynamic stability that I've already implemented. So the plan is that the bolt in the middle rotates independently, so it doesn't really matter if this chassis rotates as the head goes along, because the head can still stay still, and if the head rotates as the inside mechanism rotates, this bolt can rotate without this whole thing rotating and all the casters having to change direction. So we've actually got an incredibly smooth ride there. As it goes backwards and forwards, it can move all around, the head can stay still, or the head can rotate as it's driving. Now, this will move sideways as well to stabilise as it's driving, which is fine because it's all going in one direction. So all the casters are pointing in one direction, and then it can snake around to drive, and of course it will go slightly wider. At the moment the casters fall off the edge, but when the sides are on the ball, this will have quite a range of movement sideways hopefully, and back to front of course will be pretty much all of this. And there's still the possibility for spinning the ball round, turning the head around whichever way, so that it faces frontways on the side, and then I can move it sideways like this for puppeteering, or drive with it completely facing sideways whichever way I want. So that seems to be an incredibly smooth ride. These rubber tyres are much more cushioned than plastic ball casters, so hopefully that will be sufficient. And the head is much bigger than this. It does slope in at the bottom, but it should fit perfectly over this. And of course the head shell is attached to this bolt, and this thing dollies around freely inside. My magnets have arrived, which I've attached onto the plate that rotates, and of course that bolt goes all the way through to rotate the head shell as I said. So these are some incredibly big magnets. They're 20mm in diameter and 23mm high rare earth magnets. And on the inside of the Droid, I've got 2 more. And the reason I'm keeping these so far apart is so they don't stick together, because they're incredibly hard to get apart if they do stick together. I can show you how strong they are. They are pretty strong. So that should be enough holding force anyway. Obviously I'll put them further apart if they're too strong, because otherwise it will cause too much friction. So let's have a look at that mounted. So I've just got the bottom plate on holding the top one on. The magnets, if I take the bottom plate off, they spin round quite happily and they don't touch the surface. The magnetivity does pull down that plate, so now the magnets do scrape the surface. So I need to back off the one inside a bit, and I probably need to stick some spacers in under these casters, which is why I've left them as separate pieces screwed on, so I can raise the whole middle up, and I may need to print a more robust plate to hold them. But if I go and get into the inside and pull those away a bit, I'm actually going to get my fingers in between, then we can see that that's going to move around fine. Let's put my caster back on. It's very hard to do manually because the magnetic force is so strong, so that needs to be constrained on an arm on the inside, and then that should be more than happy to move the head around. Now of course this is a lot more heavy side to side, at least, well, heavy in all directions. It's a lot more top heavy, so this is much less stable than it was. So we're probably going to need some more ballast in the bottom, and I think I'm going to put another row of coins in on top of here, and we'll see how that goes, which will of course give it more turning force as well. It's even more of a drunken sailor than it was, and it leans this way quite a lot for some reason, maybe because that battery's on its own. So yes, that's another issue to address. That's the end of part 2. Next time I will be building the arm that moves the head around, which is going to pivot around inside. I think I'm going to use at least one 3D printed lead screw for the backwards and forwards direction, probably a servo to pull it sideways or 2, and of course a motor to rotate it. Hopefully my head dome will have turned up as well by next time, which is a specific size. I found something rather good on eBay to use for that. After I publish part 3, I'll be publishing all of the source for the code and all of the CAD, so you can build one of these yourself for free. Alright, that's all for now.